Okay, so let's welcome all of you to the final session of the conference. So it'll be, the speaker will be Kacper. He received his master's degree in astronomy from University of Warsaw, followed by PhD in theoretical astrophysics from Nicolaus Copernicus Astronomical Center in Warsaw. He then worked in several research institutions, joining University of Cambridge in 2015, the Department of Applied Mathematics and Theoretical Physics as parallel programmer and HPC administrator. He moved to Research Computing Services as a senior research software engineer in 2020. So today you will be talking about experiments with MPI benchmarks on the Intel GPU cards. So let's welcome Kacper.
So thank you very much for the invitation to speak here, and it's very nice to be in person after attending two previous marks online only. So first I need to have an acknowledgement. I didn't do that work alone. I couldn't do it without the support of many members of the staff. Our staff in the research computing services and the Cambridge Open Zeta Scale Lab, especially our data center people. And also we had some great support from the Intel engineers, and they provided our hardware. So, disclaimer, that's very much work in progress. So we are still working on it. Any numbers which you can see here today, you can please treat it as the lower limits on the performance. We are still working on the improvement of them. Okay, so the hardware. So some time ago, a couple of months, we got a test note from Intel, which is equipped with two what is the point? Oh, that's the point. Two Intel Xeon Platinum CPUs, altogether 104 cores. It has half of a terabyte of RAM, and what is most important for us, it has a 4 Intel GPU Max 1550 cards for previously known than Ponte Vecchios. They changed the nomenclature some time ago. And that is also have two for HDR200 NICs. I will be, for the full disclosure, we have also a second node, which is similar hardware. Annoyingly, it has slightly different number of cores and higher the memory. It has 1 terabyte of memory. So running between these two nodes is a little more challenging. But I will be showing here only the results from the one node. We are still working on that to have a good interconnections between the PVCs on the two nodes. I will be showing some comparison for 8100s, and our 8100 nodes is the two AMD Milans CPUs, everyone with 64 cores. Oh, sorry for the different convention. Here is the number of cores per one socket, not for the whole system. 1 terabyte of RAM, and everyone has a 4 8100 cards with versions of 80 gigabytes of RAM per card. And every node has a 2 HDR200 NICs. Again, we'll be not using here for the benchmarks. So, for software stack, I'm a little embarrassed because I'm in a Rapid user group and we didn't use Rapid, but well, that's a plan for the future. So for the compiler on Intel side, we used the latest LLVM-based compiler, 2023.1, and for the Intel for the MPI, we used the latest release of the Intel MPI, which came out in June, I think, if I remember, 2021.1. On the NVIDIA side, we didn't compile our benchmarks ourselves, OSU benchmarks. We just used the one version distributed with NVIDIA HPC toolkit, just for because it was easier and fastest. So I don't know which compiler they used, but it is the one with this version of NVIDIA HPC toolkit. For the benchmarks, we used the Intel MPI benchmarks in the version 21.3. It's the version which have support for the Intel GPUs. And we also use the modified OSU micro benchmarks in that version. Modified by us so that they support the SECU buffers, so we can use them on the NVIDIA GPUs. I was a little surprised when I look inside the Intel MPI benchmarks, because they allocate the buffers not using the SECU, which is the preferred mode of programming of the GPU class, but they use it directly using level 0, low-level calls. No idea why they did it, but it is the way. Okay, so that's the higher level stack, but for the lower level stack below the MPI, Intel MPI is using OpenFabrics. And for the Intel, we used version 1.18, which is bundled with the Intel MPI. For the Intel GPUs, one needs to use the PSM-3 provider. And currently one needs to compile it. They don't provide the distribution, the binary distribution. So, but it's freely available. And we use version 3.0 compiled with the support for one API. For the curiosity, I was a little surprised with this PSM-3. I first met it because it is part of the Intel Ethernet for a framework. And so I first met it when I was benchmarking Intel Ethernet cards, which the results which were presented here last year. So, but well, currently it still supports, it already supports the Intel GPUs, and for what is more important for us, it also supports InfiniBand. If somebody is interested, the same provider also supports CUDA. So it is possible to benchmark. But it is not possible to have it compiled with CUDA and one API or support for the Intel GPUs at the same time. There is a last component for efficient bandwidth for the large memory sizes. It is that provider needs to use the kernel rendezvous model, which again one needs to compile for your kernel, and it's using with the support for the PVCs. One thing which is nice for me as a research software engineer is that PSM-3 is actually open sourced. So if something goes wrong, I can't look inside the Intel MPI, but I can see inside the OFI provider. So it gives me sometimes a better look what's happening and to try to isolate the problem. So it is just not enough to have a provider. It has to be configured to be able to be used on the Intel GPUs. So here is the list of potentially environment variable which is of a potential interest. Some of them are for the Intel MPI. Some of them are for the provider. Unfortunately, it is not clear from the documentation what is interaction between these variables. And for example, if somebody reads the documentation for PSM-3, it is very worrying warning that if that variable is not set to 1 and somebody tries to use the GPU buffers, then the behavior is not well. They don't say anything can happen. So it's possible to get the right results, it's possible to get the wrong results. Well, behavior is not deterministic. And it is not clear from MPI documentation if any of these variables sets this variable. So, and also that variable is not anywhere mentioned in the Intel MPI documentation. So, a word of warning, please read the whole documentation, including your OFI provider. So, starting the benchmarks. So the first thing which we usually do is we count how many GPUs do we have per system. And it is not a trivial question, because on NVIDIA hardware is easy. Yes, you have 4 physical GPUs, you bought the system with 4 physical GPUs, and when you boot the system, you see the 4 GPUs. On AMD systems, on MI200 system, it is not so. If you boot your system, you will see twice as many GPUs because our operating system sees every tile as a single GPU. So if you put your systems on Frontier, when you run, you see suddenly that nodes have really 8 GPUs, not 4 GPUs. The question is, how is it on the Intel? Well, on Intel, it is chosen by the user. Because they have also the tiles, although I think they start to call it the packages instead of the tiles. But user can say that whether he will target the whole GPU, so the 2 tiles, or whether he will target the separate tiles as a separate GPUs. So it is a little similar like the NUMA architecture on the on CPU side. So in our benchmarks, we usually target the separate tiles because it is the recommended way from Intel to get the maximum performance. But you will see some figures, but it's not necessarily always the best choice, maybe. So with this choice, with so many options, it is always worth to check whether your benchmarks or your application is using the resources which you think it is using. Fortunately, the Intel MPI gives you a nice debugging information. So it gives you how many GPUs you have, how many tiles we have, and the distribution between the NUMA nodes, and then it gives you the information which for every MPI rank to which tile it will use. If you target the whole GPU, it will give you here 0, 1, for example, the 2 tiles. To affect this choice, how it behaves, there is again a set of environment variables with a very long documented and a little convoluted, how they affect each other, because they affect each other. And what was a little surprise for us is that they work unless you use SLAM. If you use the SLAM and you use the bootstrap SLAM mode, that environment variables looks like doesn't make any effect. So again, it was a little not nice surprise, but we live to that. By the way, it would be useful to have such information in a way which is completely independent from MPI. So we are working on a small utility or a library which will print that information, which you can link with your application, and it will print you such an information. Talk with me later after the talk if you are interested. Okay, so the results. So here is the latency and the bandwidth. And for the reference, the curve, that gray curve and that gray, here is the 8100 results. And we run a set of 7 benchmarks. So on every one, the tile 0 was the one of the nodes, MPI ranks, and then depending on the number, the different tile was the second member of the ping pong. And you can see that you can have a quite, first of all, the latency of PVCs is around, if I remember correctly, around 5 times larger than on NVIDIA. So it is one thing which we want to improve. We don't understand why the latency is larger. Second, you can see that latency can vary, not much, but it can vary for the small messages depending on which tile you target in non-obvious way. So I could, I could understand that the latency is the lowest for the tile number 1, which is basically the same physical device, but it also more or less the same for the sets of the tiles which is on the different physical devices, and it is larger for different sets. And it also doesn't correlate completely with the NUMA nodes to which the GPUs are connected on the host. So there's the one thing which we don't understand. The second thing is that the bandwidth for the large memory sizes is on the PVC is much lower than on the NVIDIAs. Here for the tile which is on the same devices, it is twice slower for the tiles which sits on the different GPU devices. It is 5 times slower, and that number doesn't, as far as I know, that number doesn't correspond to the hardware capabilities. So there is something wrong in our setup. So please, as I said, treat it as a lower limit. We are working how to improve it. We also tried to do some collective benchmarks. Here in all the figures, the green curve is NVIDIA's, and then the curves. In all cases, we use the all physical devices, and the difference between the blue curve and the orange one is in the blue one we targeted only the GPU devices, so we use only 4 MPI ranks, and for the orange one we used every device as a separate MPI rank, so we had 8 MPI ranks. And I don't want to comment on the numbers because I think here is, again, there is a space for improvement, but it shows you, that the bandwidth or latency of the collectives depends on how many ranks you use. So if you are a communicated band, maybe that, the determined choice of using as many MPI ranks as you can is not the best choice, because if you can target on just devices, it will go well. You will get a lower collective latencies. And that is all what I wanted to show. And we have, for our future plans, obviously we want to go to the multi-node benchmarks. We want to benchmark some applications. We hope to have some collaborations with DK to use the MPI for our benchmarks. And we also want to finish our extension to assume micro benchmarks and to provide them to the community. So, okay, thank you for attention.
Any questions for Kacper? Yeah. Wait.
Yeah, thank you. Very good talk. I have one question about the Intel MPI flag you're using. So you're using like offload RDMA, offload IPC?
Okay, that was just the set of the flags. I didn't show the values which we used.
Okay. So does that mean that Intel MPI already support like GPU RDMA or like GPU IPC?
Yes,
like
so
does?
in principle, Intel MPI supports currently the GPUs.
Okay.
And if the PSM3, you have a choice whether you want to target Intel GPUs or whether you can
is that through like PSM3 or Intel MPI itself?
Sorry?
Does it support like by PSM3?
Yes.
Or? Okay.
Yeah. If you want the support for the GPUs in Intel MPI, you have to use PSM3.
Okay, thank you.
Any other questions? Okay, so I think I'm hoping you'll have multi-node numbers very soon.
Yes, yes, we tried.
Very interesting. Okay?
Yes.
So let's give a thank to Kacper. So we'll move ahead. The next one will be a tutorial on INAM